Hello, I'm going to carry on doing a few more of the problems from this book about problem-solving strategies by Arthur Engel. And I've been concentrating on problems from the first chapter, which is about problems where you need to, or to solve them, it's very helpful to find an invariant or some quantity that is related to what you're looking at. That usually helps you decide whether some process terminates or can achieve its goal and that kind of thing. I've been trying to get more and more systematic, and sometimes I've had some success. I've had an experience after several of the problems recently where people have pointed out considerably simpler solutions to the ones than the ones that I've found. And I've been reflecting a little bit about that, and I think it means that I could be honing my technique a little bit. And I think sometimes if I just dive in too quickly and try to just experiment around and I greedily go for the first solution I can find, whereas if I just paused and reflected a bit more and maybe looked at the problems in a slightly more abstract way, I might actually save a bit of time. It's a riskier strategy because if you don't find a neat solution, then you can end up not getting anything. Whereas if you dive in and are sort of a bit more greedy and do several calculations, then you're more likely to get something, but you're less likely to get, so to speak, the right proof. So today I'm going to try. I don't know how successful I'll be, but I'm going to try to be a bit more systematic and a bit more reflective and trying to get to the essence of the problem before I really sort of go for it. So let me share my screen and then I'll write down what the first problem is that I find in the book. First problem that I haven't done. And it reads as follows. The integers from 1 to 2n are arranged, I think those were the next two words, in any order on 2n places numbered 1 to 2n. So we have a permutation of the numbers from 1 to 2n. Now we add its place number to each integer. Okay. Oh, by the way, this, for what it's worth, this is question 18 out of 60. Prove that there are 2 among the sums which have the same remainder mod 2n. Two among the sums that have the same remainder mod 2n. So I feel as though this should be not too hard a problem if I'm sensible about it. So this looks as though it might just how's this going to be anything to do with invariants? That's the question. So that should give us a clue somehow. So for example, can we say that, let's write down, so I've got the numbers a1 up to a2n, and those are the numbers from 1 to 2n in some order, and I can think of it all as being mod 2n. And now I'm looking at the numbers a1 plus 1 up to a2n plus 2n, and the aim of the game is to prove that those are not all distinct mod 2n. So is there something that we can't get? Clearly not, because if I want to get some number x, I can obviously get it just by, well, I could get it by choosing a2n to be x, for example. That would be the sort of simplest way, but I can also get it in any other way. I could choose a1 to be x minus 1, and so on. So there's no way of ruling out any particular things. I can't just apply pigeonhole like that. And in fact, what am I saying? Because if I could apply pigeonhole, that would already be telling me that they weren't all the same. But could we prove something like, so but the fact that n has to be even seems to be suggesting some sort of parity. And I want to ask myself whether more of these numbers have to be even than odd or something like that. So maybe we could just look. So when n equals 2, I can either go for 1, 2, which then when I add the place numbers I get, but maybe it'd be slightly more convenient to make it 0 and 1. So I'm working mod 2, so 0 and 1. If I add the place names, I get 0 and 0. If I started with 1, 0, and I add the place numbers, then I get 1, 1. So that's place number 0, and that's place number 1. So either way, I get the two being the same, which is obviously going to happen there. But I can't say that I've got more evens than odds, because here I've got more evens than odds, and here I've got more odds than evens. So that doesn't quite do it. So let's have a look at, say, 0. I'm now going to look at mod 4. So 0, 1, 2, 3, that's just going to double everything. That's clearly not going to work. What if I go for 0, 1, 3, 2, for example? So that goes to, now I'm going to add 0, then I'm going to add 1, then I'm going to add 2, and then I'm going to add 3. So I nearly got there, but just at the last minute, things messed up. And here I've got the same number of odds as evens, so that's not helping. Now can I look at this in some more abstract way? So I haven't even proved it in the case where n equals 2. So perhaps I should try to do that, because that may actually give me a clue. Can I say anything without loss of generality? Can I say without loss of generality I start with 0? I think so, because if I cyclically permute everything, then that's just going to add a constant over here. So if I cyclically permute 0, 1, 3, 2, just to illustrate that, if I went from 0, 1, 3, 2 like that, then I would now be adding 1 to this 0, and then 2 to this 1, and 3 to this 3, and so on. So I'll get, instead of 0, 2, 1, 1, I'll get 1, 3, 2, 2. So it ends up cyclically permuting the answer and adding 1 to it. So that's sort of potentially interesting. I think I might have spotted a I suppose one other, No, I spotted something, but it was a potential argument. But I'm not going to articulate it because I realised that if it worked, it would also work for odd, and we know that this will not work when we have an odd number of things. So, for example, the trivial case of 1, but also if I had such, say, 0, 1, 2 mod 3, that would go to 0, 2, 1. Just double everything. So, and that construction clearly works for every odd number of things that we permute. So, something to do with it being even, very clearly. But that just tells me that the really sort of obvious thing to do doesn't work. But I still need to think about an arbitrary permutation. But let's just go back. So we're adding the numbers 0. Well, yeah, let's go back and look at this. These must all be, if we want all these to be distinct, that's telling us that AI minus AJ must never equal J minus I, because then AI plus I will equal AJ plus J. Is that a helpful way of thinking about it? We could ask an equivalent problem which is, so this is mod n of mod 2n. I mean, if instead of adding 1 up to 2n we subtracted 1 up to 2n, then that would look a little bit nicer. It would then say AI minus AJ should never equal I minus J. So why is it that if I permute, I must be able to find two things where the difference after the permutation is the same as what it was beforehand? If it's even, that's a rather interesting question. On the face of it, I don't see any reason at all. And again, I'm still puzzled by the idea that there should be an invariant involved here. What sort of invariance could there possibly be? So what we've seen here is, for example, in this case of 4, you can't, it seems to be difficult to rule out any individual differences, and it's not much of, I can't see an obvious pattern in what you actually get when you do this addition. But maybe one could think about it in the following way. If AI minus AJ, let's just draw a little graph. If AI minus AJ equals I minus J, that's telling us that it crosses, that we some line with gradient 1 Is this going to help? I don't know. Some line with gradient 1 contains 2 points. So what we're actually asking for is the following. We want to have a set of points in 1, 2, or 0, 1. I don't see why this should help, because it seems like a trivial reformulation of the problem. Nevertheless, I feel that's a nice way of looking at it. So 0, 1 up to 2n minus 1. And what are the rules about the set of points? Well, we've got to have a graph, so there's got to be a point in each column. Exactly 1 point in each column. There's got to be exactly 1 point in each row, because this function is meant to be a permutation. So this is the function I maps to AI. And finally, we're not allowed to, if we're going to avoid this thing, we're not allowed to have 2 points in the same diagonal line. Where by diagonal line, I mean one that wraps around. So it goes up to here, and then comes down to here, and back up to here again. But there may be something funny going on with these diagonal lines, because how many points do you get in a diagonal line? And how many diagonal lines are there? That would be straightforward if n is odd. Is there something annoying that, I mean, but potentially useful? If n is even? No, because they're all of the form y minus x equals lambda or something like that. And so there are 2n of them. It's one for each value of lambda. So I actually still don't see why you couldn't just choose those points in a nice way, so that you had no 2 in the same row, no 2 in the same column, and no 2 in the same diagonal line. That is still quite interesting. I normally say a bit more than I'm saying at the moment, but that's because at the moment I am more stuck than I've been typically in these questions. I feel as though I need some interesting new idea, but so far I still like this picture. In fact, I think maybe this picture will help me think about the case where n equals 2. In other words, we've got 4 points. So let's just draw a nice grid. And so the sets that I've got to, so I've got to have a permutation matrix, so to speak, or a point in each row and a point in each column. But I've also got to make sure that, for example, I've got exactly 1 point in this diagonal here, exactly 1 point in this diagonal here. Maybe I'll just loop that round just to indicate what's going on, and then 1 point in this diagonal here, and 1 point in, I'll just make that with a curly line so we see that that's one diagonal. So let's decide. I think I can, without much loss of generality, I can assume I've got this point. How many points is that going to rule out? It's going to rule out all those 3, all those 3, and all those 3. That's actually quite a lot of points that's ruled out. Is that going to be a clue? So I'll put little crosses on all the points that are no longer allowed. The fact that it's a lot of points should be irrelevant, because that, again, we want something to do with parity. So now I want to find, out of these remaining 6 points here, I want to find one in each row, one in each column. I don't want to have 2 in a diagonal. But notice that I've completely removed this diagonal. How many diagonals are left? There are only 2. Oh wait, sorry, what am I talking about? That goes with that. So those 2 points form a diagonal. Those 2 form a diagonal. Those 2 form a diagonal. So it still doesn't look necessarily impossible. But if I choose any point, it's going to rule out 1, 2, 3 other points. So let's just arbitrarily pick one. I'll pick that one here. That's going to rule out 1, 2, and 3. And now I'm left with 2 that are in the same row. But why did that happen? Had I picked this one instead, this is going to be unpleasant to draw. Maybe I can just... Then it would have ruled out everything here, and it would have ruled out this, and I would have been left with, I think, that one and maybe that one, which would, oh, maybe those 2, which would have been in the same diagonal. So it's still, I'm still finding it unclear what's going on. But I am slightly wondering whether, having chosen the first one, I'm now in a situation that I can argue is hopeless. So let's try that actually. So I'm going to assume that I pick, because I'm almost certain this is not losing any generality. So I've got my numbers from 0 to 2n minus 1. I'm going to assume that I pick 0, 0. So that rules out all of this, and all of this. So what's the remaining task? So now I have to pick A1 up to A 2n minus 1. And still the condition is that, oh, I've got 2 conditions. So AI doesn't equal I, and AI minus AJ doesn't equal I minus J. Is that any easier to think about? I've suddenly had a thought, which is, we're trying to prove that the number of solutions to AI minus AJ equals I minus J is not 0, and this is a parity is clearly relevant. Might it be easier to prove that the number of solutions to this is necessarily odd? So the number of pairs ij such that AI minus AJ equals I minus J is always odd. or something like that anyway. Is that going to be the case? I feel as though that might be rather easy to find a counterexample too, actually. So if we just chose, let's say with 6 or something, supposing we went 0, 1, 2, then we've got that 1 minus 0 equals 1 minus 0, 2 minus 1 equals 2 minus 1, and 2 minus 0 equals 2 minus 0. And now if I go up, so 3, 4, 5, I will not choose. I'll go for 4. Just 4, 5, 3 or something like that. That was not a good choice. 4, 3, 5. What's that? What was that done? 4 minus 2 does not equal 1. 3 minus 2 does not equal 2. 5 minus 2 does equal 3, so I've got an extra pair there. But 5 minus 1 equals 4, but 5 minus 0 equals, so I've got an extra 3 pairs, so I've got an odd number of such pairs. Oh. So I had some trouble finding my hoped for counterexample. So now I'm going to work with that as a hypothesis and see if I can prove it. And the way I want to see if I can prove it is, I'll start with 0, 1 up to 2n minus 1. And I'll just see whether the parity of the number of pairs such that ai minus aj equals I minus j is an invariant. So if I swap a couple of things, will that, well, perhaps I'll go for a1, a0, a1, a2, up to a2n minus 1. So I'm slightly encouraged by this because it's, at least I'm thinking about an invariant. I don't know whether this particular one's going to work, but it might be something along these lines, some sort of parity idea. So if I swap a1 and a2, so now I can get any permutation by swapping consecutive things. So if I swap a1 and a2, what effect is that going to have on the number of pairs? Well, let's just have a look at the set of ij such that ai minus aj, perhaps it's slightly easier to think of aj minus ai equals j minus I. And I might want to make it the set of I less than j or something like that, because in fact, that does make sense, because I don't want to double count. Because if I double count, automatically I'll get an even number of pairs, obviously. So I want unordered pairs. So if a2 minus a0 equals 2 minus 0, so if a2 minus a0 equals 2, I'm going to lose a pair there, but then but if a1 and a0 have nothing to do with each other, I will not change the relationship between. So if I had sort of 0, 2 and 13 or something, then swapping those two looks as though it changes. It loses a pair that had the property we had, this property aj minus ai equals j minus I. And then anything over here that any r such that ar minus a2 equals r minus 2 will also lose we'll lose that pair. And it's not quite clear why putting the A1 here is going to make much of a difference to the number of pairs involved A1. So that hoped for invariant doesn't really look like an invariant to me. But something like that might potentially do it. It's a little bit like one of those problems about queens on a chessboard. You want to put pieces. It just suddenly occurred to me that yeah. So imagine you have a queen, but it's not allowed to move diagonally from top left to bottom right. It's only allowed to move diagonally this way, but it can move horizontally and vertically. So then the question is, can we put 2n queens on a 2n by 2n chessboard? 2n of these slightly restricted queens, such that no two of them attack each other. Having put it like that, I'm absolutely convinced that there are people out there, I mean, I know even who they are, who will find this problem laughably easy because they know all about mutually attacking queens on chessboards, which is a much studied problem. Unfortunately, it's not much studied by me. So there is an elementary argument that I'm not getting. I feel because n is even, it's got to have something to do with the fact that n plus the multiples of n, there aren't 2n of them, there's just 2 of them, and or indeed the multiples of an even number, there are n of them rather than 2n of them. So I wonder whether if I were to look at the black squares and the white squares of my 2n by 2n chessboard, and whether that would for some reason be helpful. So for example, can I, just going back to the examples that I've found, though, I've got to be a little bit careful not to so this 0, 1, 3, 2 so I have my 4x4 board. How many black squares can I fill? So if I fill that one, that rules out 1, 2, 3 further black squares. Sorry, more than that. It rules out all of those and those 2. So I'm not allowed that one, not allowed that one, not allowed that one, not allowed that one, not allowed that one. So there are just 2 possible black squares left, it would seem. And that's a bit of a disaster because I'm supposed to be, oh no, it's not. So let's just imagine I put one in there. which is a bit silly because it's not a black square. Hold on. The two that I've got left are here and here. So if I put this is not losing much generality, if I put a black square there, that rules out this one. But that's okay so far. Now let's just see which white squares have been ruled out. I'll put a different symbol in for ruling out a white square. I'll put a little line like that. So I can't do that, 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 can't do that. And so all that's left, that was black, but that's now been ruled out. So there's just one white square left. And so could I argue somehow that if I've filled up half the black squares, at least, then I've ruled out more than half the white squares? That seems a bit strange because or does it? So I think I may be thinking along sort of reasonable lines. So if we fill n black squares, I'll define a black square as one where the sum of the coordinates is even, and a white square is where the sum of the coordinates is odd. Then, which we can do, then we rule out n rows and n columns. And I think we can't fill more than n black squares because there are only n diagonals. There are only n black diagonals. That's an important point there. So only n black diagonals. So in fact we know that we've got to fill in n black squares and n white squares, and we're very much using the fact that 2n is even, because otherwise the notion of black squares and white squares mod the number that we have would not make sense. So now we have effectively an n by n board, and we need to fill in n white squares, and no two of them are allowed to be in the same row or column or diagonal. But how many diagonals do we have? Let's just have a look at the 4x4 case again. I'm just going to look at a very particular case. So let's say the black squares are these two. So I've filled in that one and that one. So now my only white squares left. So it's got rid of all those two rows, those two columns. Sorry, I wasn't allowed to do that because they're in the same diagonal. Oh, well, let's make my diagonals the ones that, just for the sake of this particular diagram, the ones that go in that direction. So, because it doesn't make any difference. So I fill in those two, and now the only two white squares that are left are going in the opposite direction. There's only one diagonal left. Is that going to be a general phenomenon? Let's try it with 6. And this is not going to be a rigorous, even an attempt at a rigorous proof. It's just a little experiment. And the reason I'm doing the experiment is I want to see whether there's a lemma that's worth trying to prove. So now, again, I think it'd be nice to say that the diagonals that I mustn't occupy are the ones that go in that direction rather than that direction, because that means I can just nicely put in 3 black squares. So now I'm stuck in this half with white squares, and so the white squares are those ones. And how many diagonals have I got? I've only got 2 diagonals left. So it's sort of looking as though that might be a true statement. So what's the statement I'm claiming? I'm claiming that if you rule out so when I choose my black squares, I am choosing what can I say about the diagonals that they belong to, given that I've got a permutation? So let something like A equal the set of I such that AI minus I is even, and suppose that A is greater than or equal to n. In fact, we might as well make it equal to n. We know that if we've got to occupy every single diagonal, then it's got to have size n, and then the complement's going to have size n as well. So then let B be the set of AI such that I belongs to A. And the question that I'm asking myself is, how many so A is going to be the set of columns that I choose, and then B is a set of rows that I choose when I've filled in my n black squares. So how many diagonals, so how many values of AI minus I can there be with I not in A and AI not in B? What I'd like to show is that it's strictly less than n. sorry, I didn't mean to say AI minus I because I haven't yet chosen that. So perhaps it's slightly clearer to say y minus x with x not in A and y not in B. Oh, and also, crucial extra detail, y minus x odd. And we know that we have a map, which I'll call A because it's from A to B, such that AI minus A of minus I is even for all I in A. So we've got some pairs A goes to B. So what we're asking is, if we look at A complement and B complement, I have a horrible feeling that there might be a really simple solution after all this. What if I just look at the sum of AI minus I? I'm annoyed with myself now. It equals the sum of AI minus the sum of I, all mod n, but that's a permutation, so it equals 0. So is that reason enough to be annoyed? So if these are all distinct, that's telling me that naught. So if these numbers are in fact the numbers 0, 1 up to n, then I need that 0, 1 up to 2n minus 1. Naught plus 1 plus 2n minus 1 is congruent to 0 mod 2n. Is that false? I get 2n minus 1 times 2n all over 2, a multiple of 2n. I hate myself. So if n is even, that's odd, and it would have to be a multiple of 2. Doesn't happen. If n is odd, then that thing is even and it's all fine. So we've done it. Well, I had some fun reformulating things, but why did I not think of writing this down right at the beginning? And why did I think of it suddenly now? Let's just try and go back to that, because I somehow was having the feeling, okay, I think I was trying to reconstruct my thought process, because that's the bit that really interests me here. So I somehow had the feeling that if these were all even and those were all odd, that some sort of parity thing would lead to something going wrong. Actually, I think what was leading me slightly astray was it's not really the parity of these AI minus i's, it's just the rather stronger condition that they all have add up to 0 mod n. And it so happens that the parity of this 2n affects whether that's possible. So parity does come into it, but not quite in the way that I was expecting. I haven't given a very good account of why I suddenly thought of writing this down. I'm not quite sure what lesson to get from that, but anyway, I'm relieved that I didn't have to give up. I think I shall stop this video with just that one solution. But somehow, again, I suppose the process of exploration was of some interest, at least to me. But it's time to stop. Thank you very much.